so we had a question on subsets. Just do untitled R markdown. All right. Let me load my data set. And I'm sure I have it. I've got it on this computer. Gambusia. Strings is factor, heading yes. All right, so I've got my data set in here. Oops, we should do that. So I can see basically from the description that it says I have 4 levels of month. Month is a factor with 4 levels. Sex is a factor with 2 levels. It's keyed out as F and M. And this kind of shows you how R recodes it. So it takes the text that we had, F and M, and R changes it to like 1 and 2. But that's okay. We want M and F, and then length is a numeric vector, and richness is a numeric vector. It's actually an integer. So that question asks you to first only look at female fish. Is that right? All right, so what did the homework have you do? What did it tell you to write?
The average length of the female fish in the 4 months of collection fish, so then which month we use the average length of fish.
Yep, so which ones differ, right, for the female fish? And then I give you a note, right? Like how you're supposed to do this. Is that right? So I didn't have that updated. I thought I really. I can't believe I did that. Go to my homework file. Guesses because we would have introduced. So here's our code for extracting female fish, and I'll do like fish.f will be my new data frame. Actually, it's already called Gambusia, at least for me. So I'll use Gambusia.f. And what we're doing is we're going to save our data frame. And we're going to use the subset function, which is subset. Now, subset's going to subset an object that we give it. So we are going to give it Gambusia because that's a data frame. All right, so when we give it a data frame to subset, R will return a data frame to us. So this Gambusia.f will be a data frame, and it will have month and sex and length and richness in it. But we only want to extract female fish. So the format for this subset function, I'm going to say new dat, is subset data and then a logical, where our logical is a statement, and I'm going to say selection statement, where we tell R which rows to pull out based on this statement. So it will tell R which rows to extract. based on our selection statement. Now, the format of the statements is this. It's variable equal sign and then level, right? And it's 2 equal sign. So the variable, that's our variable name that is in our data frame. Double equal sign, this is the logical that means equal is equal to. And quotation marks level, the group level within our variable name that we want. All right, and it's going to be in quotation marks because we're specifying the text version of it. So we want to extract the female fish. All right, so here's how to extract all female fish. We're subsetting our Gambusia data set. That's our data frame. And now we need our logical statement. The logical statement is going to be variable, double equal sign, and then the level. So what's the variable name that we're going to give it? Is that the variable name? X, double equal sign, and what's the level that we're going to give it? F. So F is in our data frame. So that sex variable, sex variable, that's a variable that we're selecting on. We're removing out all of the ones that have an F on it. So if I just go into our Gambusia data set, here's our data set here. R is basically going to go row by row. And our logical is sex equals F. So it's going to go row by row. If it doesn't have an F in there, then it skips it. And then once it has an F, it says, okay, here's one. I'm going to save this row, and then I'm going to go into the next row. Now we toss it out. Then we're going to see the F in this fourth row. It's going to say we're going to save this one, and this one, and this one, and this one, and throw out all the M's so that when we run this then, so Gambusia F, and I look at Gambusia F, you will see that we only have female fish in our data set. We only have female fish in our data set. So we went from Gambusia that had 405 observations, so 405 rows, and now we only have 325 rows in our new data set. So now that we have Gambusia.f, we can go ahead and run our, let's say, QQ plot. I need to load the car library. So QQ plot of, we're doing length as a function of month, where the data that we're going to now use is Gambusia.f. So this will only be our female fish, and we'll get all of our QQ plots that we need. This subset will not be on this exam. That's how we use our subset function. I thought I had stated how to use that. Edit it. My data frame. Gambusia.f is subset subset Gambusia 6 equals. All right. So we have it here, and then I also posted that code on part of the homework side. So it says, here's the code. Hopefully, copy and paste it. Questions? All right. Exams this week. Closed books on Wednesday at 11. The application part's a take-home part. So that goes live at 3 o'clock today. It's going to be due by 12:30, so if you have issues knitting it, we can address it on Wednesday. Hopefully get it knitted to a PDF and then upload. All right. The quizzes. I don't think I have that ANOVA going live yet. Let's make it go live. So quiz 9.1 and 9.2, that's the Z test, T test, and then doing stuff like T test and sign test in R. I've upped it so that you can have another attempt at it. So it kind of gives you additional practice. And that first quiz was 10 minutes. I bumped that up to 15 minutes. You should have enough time to kind of go through and do it. You have the data. I'd get the R script set, I'd load your libraries, have the data file imported, all ready to go, and then you could start. I will make this ANOVA one go live right now, which is, it's a single like ANOVA to kind of step you through. So you can do that today. You can do that, after our class before the lab, or you can wait until 3 o'clock when we're done with our lab to kind of work through it. That's also kind of a check to make sure you're doing the step of the ANOVA properly. All right, this is kind of in preparation for the exam. Yep.
Is that a quiz or homework?
There's a quiz part. So this part was going to be the homework that you can work through. And if you get through these and feel comfortable doing it, the quiz part's going to be pretty easy. But the quiz will be the check to see, are you able to do your QQ plots normally? Are you able to, do you know what your next equal variance test is, which one to run, and how to run it, how to interpret it, and how do you run the ANOVA, and how do you do all of that stuff. So that's what we're looking at. Questions? So while we are at it with this homework, we worked through, we did an ANOVA example in lecture, and then we did the fish length text, and we kind of had to rush through the output. So now we have this homework, this Gambusia homework. So what I want you to do is work on this first problem, Gambusia. Run through your test of the assumptions, do your test, and really, even if we violate the assumptions, just keep going as if all of our assumptions are met. I want you to run through post hoc test if appropriate, and then we'll check it. I'll put up my answer, so that way we can make sure everyone's on the same page for this game. And we have the script, that subset, to pull out all the female fish, so we'll use our female fish. take about 10 minutes or so. ANOVA does not take this. It doesn't take an equation. The ANOVA function takes a linear model. So a linear model generates all the information needed to calculate the p-values. So it's a two-step process. We have to first to make that model and then run the ANOVA. is in your model. So get length as a function of that. General. And then use some. I don't think that'll be a summary of that. So that just returns the estimate, and then the summary will give the rest of the information. I've done it, only compares it to a control. So, and we're not really going to use that on any quiz or exam. But it's presented in case you ever need it. Like you have a control and then treatment groups. And I could always help you get it refactored. We'll talk about refactoring in the grad stats course. But if you need to get it refactored so that control always appears first, I can show you how to do that.
So I wasn't clear either on, instead of listing them out, which are different, because then something are better rates.
Yep, I'll show that up here again.
Will you accept it? After that?
Yeah. All right, so how's it going? So I checked my QQ plots, look good, right? Maybe just one, maybe January, but we've got 4 groups. All 4 groups based on these normality plots look good. So, that was our check. So we pulled it out. So step 1 was assess normality. What's our conclusion? Data are normal, right? So then we have to assess equal variances. And for that, we're normally distributed. So do we run Brown-Forsyth or do we run a Fligner-Killeen test? Brown-Forsyth, right? Normally distributed. Go for the Brown-Forsyth. It's more powerful. So we access that using Hsd Test. Center equals median. And I get this output. So we're normally distributed. Do we have equal variances? Yep, p-values 0.7697, so it's greater than 0.05. We conclude that the variances are equal. So our assumptions are met. Now we run the ANOVA, generate your linear model, view the ANOVA table. I get this. So, do the lengths differ between the months? Yeah, they do. So remember, our null hypothesis for ANOVA is that the means are equal. Here, we reject that claim because our p-value is pretty small. So we know the means are different. We just don't know which ones are different. So now we go to our two-key Hsd test. So I run two-key Hsd AOV over mod if I get all of this. And this is actually pretty easy to do because when I look at this, I see p-values, or adjusted p-values, are all below 0.05 except for one comparison, and that's November to March. So I can write a fairly quick, I'll do a summary. So this isn't the full write-up, but for the write-up of this part, I could say something like this, that average size was similar in the March and November collections, and do P adjusted, P ADJ. I guess I'm going to put those in braces. It's weird thing using those. And I'll just put equal to 0.99. So average size was similar in the March and November collections. but sizes differed. Oops, and sizes differed. And mean size differed between all other comparisons. All other monthly comparisons. And this would be P adjusted is less than 0.04 because I go to my highest P value at that point, which was January, February, and say everything was smaller than this value. And I'm just specifying that we ran the additional comparisons. So I didn't have to go through and list every single p-value. We know that there's only one comparison that was not significantly different. That comparison was March and November. After that, everything else is different. So we just have to specify this one comparison is not different. What about the rest? So
When are we supposed to do like the lines of
that's what we're gonna go through. January, February, November, January, February, March. All right. So to do the lines above, what I'm gonna do is look at my aggregate function. So look at the averages, and I'm going to arrange them in order from smallest to largest. So we have January, February, we have March, and November. And this is useful when we have a bunch of different, some means are different, some means are not. Especially as we start getting to 5 or more groups, this will be useful. So I have them arranged in order from smallest to largest, and then I'm just going to start looking at our comparisons. So I look at the January and February line. So from smallest to the next smallest, and the p-value is less than 0.0005. So I'm going to start with the line over January, but I stop because we're different from February. And since I've arranged everything in order, if I'm different from the next closest value, then that means I'm going to be different from every other value that's larger than that. So I stop my line, and then I go up to the February. So now our next comparison is going to be February through March. So you go February, March, there's my comparison, and I get a difference. So I start my line, and then I have a break, because again, February to March. March is the next highest number. If I'm different, if these two are different, then I know February and November are different because that's an even bigger difference. And then I go to March to November, November, March. Those are not different. So now I will put a line across. And this just kind of helps to visualize which ones are different, which ones are not different. So I like doing that one because whoops. Move that out of the way so I can access it. This was our fish length. This was our example. We did it in R. All right. We know which ones are different, but we normally present our data as figures, right? Graphical display or table display. So this would be a summary figure. We've got our average length, we have our lake. All right, I added my error bars, which would be standard errors. All right, and they look different. But how do we incorporate the information of our statistical test into a figure like this? Well, what we can do is use subscripts. So I've labeled each of our points with a subscript, A's, B's, and C's. And in the text I say, lakes with similar letters are not significantly different from each other according to a Tukey's Hsd post hoc test. And that means that our p-value is greater than 0.05. So in our R document, in the RMD file, go back to here. Did I already close it? I did. I already closed it. So in the RMD file, you go back and we did those lines over our figures. So we did the same thing. We put them in order, and then we started doing our lines, and that helped us keep track to say, okay, well, Ram's Head and Green, they're not different, so they're going to receive the same subscript. Green, Mallard, and Big Bear, they're not different. They're going to receive the same subscript. And then Deer is different from the rest. It gets its own subscript. And it shows you then that Mallard, or Green Lake has both A and B attached to it because that lake is similar to all four of these. It's just kind of like that middle one. So yeah, in the text we have to specify and clarify which ones are similar or which ones are different, which I do, but we need to do the same thing in a figure, and that's where those lines come into play. It's easier to kind of gather our thoughts when we have 5 or more groups. 4 groups could also be a little confusing, but when you looked at that, when you looked at the post hoc test for lists, we had, how many different comparisons did we have? We had 10 different lines in that Tukey's post hoc test. That's 10 different p-values we have to keep track of. In this Gambusia one, we had 6 different lines. It's more manageable, but it could still be a little confusing if we've got a mix of significant and non-significant p-values. Here, it's pretty easy. But yeah, the lines make our comparisons a little bit easier. And you'll see this in the journal articles if you've been reading them for various classes. You'll see things like this being presented. All right? Do you have to report this? No, you don't. I'll take it as long as you kind of specify which ones are different. Do the interpretation.
Like if it works significantly different, like you want to report it because.
Yeah. So let's say the ANOVA was not significant. The original ANOVA was greater than 0.05. We don't run a Tukey's, so we just have a figure like this with no subscripts, and we just say average lake, average fish length for these 5 lakes. No difference was detected between them. So we would say something like that and include the ANOVA. If all of them were different, I wouldn't use subscripts. I would just say all of them are different. Or if only 2 of them, so like with our month, let's use this one as an example. Let's say these 2 were the only ones that were not different from each other. I could put an asterisk on these 2 and just say the 2 means with an asterisk are not different from each other. And that's it. So there's different ways. If you're doing this for a research project, come talk to me. I can help you make these. Because I also include the script on how I did this in R. I've cleaned it up a bit, made it a little bit more automated, but this was the entire, all of the lines of text that would produce this graphic. As you can see, it's probably a little bit easier to do it in Excel. And then make a text box, insert text box for your subscript. A little bit easier. It is.
Wait, go back to that other screen.
Which one?
You had like on the blue one.
Yeah, I'm gonna show this slide. This is what we did with our lines. So this one.
Yeah. When you know when to use the budget was being versus the fund versus the
So the standard error gives us a standard error for each of our groups.
and
So what I have to do is I have to calculate the error bars. So I use the standard error for the error bars. So for here, our error bars, so we have our mean, and then I told it we have to go above, that's a standard error, and we have to go below, that's a standard error. So I had to calculate the standard error to know how much above and how much below to do it. And each one's going to be different. So you can see this standard error is wider than this one. And that's what we should have. Yeah, there's ways. I can always help you out. It's a little bit easier in Excel. Questions? How was the Gambusia? Did you feel confident doing that homework? That one? Maybe? All right, so we have the other problem that you can work on. We can go through that in lab, and then probably we'll let you'll have time to do the ANOVA quiz just to kind of check yourself. In our presentations, that's how I was a little late today, I'm sure you noticed, I have this. Under the assumptions are violated, I made an RMD file, posted it, and this is it, where I've wrote out some of the notes, so hopefully we can you don't have to sit and copy everything. I've got it up there, but I do have spots that are open where we'll run the text, talk about the write-up, we'll talk about the interpretation, so you can add notes and stuff. This only goes up through violation of equal variances. So if we violate equal variance, what do? I think that's the easy one to run. And it also has a nice setup for subscripting or subsetting our data set. So this is we'll be a little bit more specific on how we do subsets because we need to learn how to do that. So you can download it, have it ready. But I think what we'll do is we'll stop here. And you can work on that second homework question, which was pesticides. All right. So you do pesticides, and then what we'll do is we'll go through pesticides and see how you're doing. Since this is exam 3. All right. All right. See you too.